I'm Becky.
I'm Jackie.
And we're here on this Google Hangout. We'll be here for approximately the next hour, and we'll talk about some of the questions that came up in the discussion forum, and we'll talk a little bit about your first quiz coming up and other stuff. On the right-hand side, if you're coming in on the Google Plus, there's a question and answer palette, so you can type in questions that you may have as we go live, and we'll attempt to answer those as we go along. Let's see, to start off, I think, Jackie, you're going to start off, and we'll take it from there.
Okay, I need a minute to prepare the actual lecture, but I'll do the introduction part, okay? My name is Jackie Mankiewicz, and I was the teaching assistant last year as well, and for this course, and I am a graduate student in the School of Earth and Space Exploration at Arizona State University. I actually work on, I'm what's called an observational astronomer. There are 3 classes of astronomer. There are observational astronomers, theoretical astronomers, and then instrumentalist who build the cameras or other instruments that we use to obtain the data. So I'm an observational astronomer. I obtain the data. And I specifically work in optical, visible light astronomy, and also in radio astronomy. I use telescopes like the 2-meter mirrors on Kitt Peak in Arizona, or radio telescopes like the Very Large Array in New Mexico, and I use them to look at galaxies and to study cosmology. And that's me. Becky?
Becky, why don't you introduce?
I'm Becky Jackson. I am also a grad student in the School of Earth and Space Exploration at Arizona State. I am in my 4th year, so I've got a couple more years to go. So I'm an instrumentation astronomer. Right now I'm working on testing an infrared camera, so it works in the near infrared, and a small telescope that would be available commercially. We're trying to get really good resolution and precision so that we can explore and characterize exoplanet transits. Exoplanet transits are when planets in other solar systems pass directly in front of their stars, and when they pass directly in front of their stars, a little bit of the light is blocked, and we look for that little dip in the magnitude or the brightness of the star, and it's basically figuring out characteristics about the planet based on that. But right now it's mostly getting the telescope and the camera to work together. So that's pretty much what I do.
Okay, I'll do a little introduction, give Jackie a few more seconds. If not, we'll go to Plan B. So I'm Frank, and I guess you're super lucky in this class because you've got, as Jackie categorized, you've got all 3 categories here. We've got an observer, we've got an instrumentalist, and I make it all up as I go along, so I'm a theorist. And I'm the instructor for the course, and that's a little bit about me as far as this course goes. You ready, Jackie?
I could use like 2 more minutes.
Okay. I shall yammer. Let's see. Okay, so I did my undergraduate at University of California, Santa Barbara. I was a physics undergraduate. And then I went off and worked in Silicon Valley for about 4, 5, 6 years. I did not start Google. I did not make $1 billion in Silicon Valley. But it was a very interesting experience working in that area. And then I decided to go back to grad school at a relatively older time. And so I did my graduate work at UC Santa Cruz. And I think one of the reasons why I like the program at UC Santa Cruz is because it was both observational and theoretical. So I have been on a mountain several times. I have invented a telescope. I'm just not any good at it. So I do what comes best for me. Let's see, and then what did I do? So after graduate school, I did what's called a couple of postdocs. So I bounced around at different institutions for about 3-year periods. I've been at the University of Chicago. I've taught at the School of the Art Institute in Chicago. I've been in Clemson, South Carolina. I've been in San Diego, California. I've been in Los Alamos in New Mexico. And then I came to Arizona State in 2008, and I've been teaching online for about the last 6-7 years or so. And that kind of brings me up to the present of where I am. So my specialty is stars. Research-wise, what I do is stars, particularly stars that go boom in the dark night sky, so stars that explode, so supernovae, novae, little smaller pop cousins, gamma ray bursts, basically anything that goes bang in the night will kind of get my attention research-wise. So that's a little bit about my past and what I do. Ready, Jackie?
Okay, sorry, I have some. Get out of here. I have some dogs, and they're loud. Okay, so there'll be some racket while I do this explaining. So I am here to talk about constellations, and I think one of the things we don't cover in this course is how to find your way around the night sky. And I think I'm going to do just a little bit of that. I'm going to give you some resources so that you can do it on your own after I've given you the little walkthrough. So first of all, a very excellent resource for learning your way around the night sky is, can you guys hear me? Okay, awesome. Okay, so a really excellent resource for finding your way around the night sky is let's see if I can get it in the picture here. This is the Audubon Guide to the Night Sky. There are lots of guides out there, but this is actually the one that we hand out for the in-person labs at Arizona State University. We also ask people to purchase star wheels, and they come in a variety of sizes and orientations. You want to find the star wheel that matches your latitude on the Earth. So this actually isn't completely correct for Arizona. This is 30 to 40, so this is correct for most of the continental United States. But I'd want the 20 to 30 degrees of latitude for Arizona. If you're in the southern hemisphere, obviously you'll want one that's appropriate for the southern hemisphere. I actually have one of these, the Australian Sky. I got this ages ago when I was in Australia, and it's really, really old. It's really beat up. And I don't think they published this particular book. So if you really want me to make some recommendations, I researched this last semester, and I found some excellent star guides for the southern hemisphere, and I can put those links on the discussion board if anyone's interested in that. But for the northern hemisphere, I recommend sticking with the Audubon Guide, and it has all sorts of cool. It has pictures of every individual constellation, and then it has the different months and seasons and what's up in the sky, and then it just has lots of random cool pictures of different astronomical deep sky objects, and it has useful information, pages and pages of information on all of these objects. So it's a great book, and I actually would purchase it even if you are in the southern hemisphere, just because it's full of awesome stuff. I'm going to give you a tour around the northern hemisphere first, and then we'll switch to the southern hemisphere. This is going to involve a screen share, so you'll be able to see what I see. So the first thing I'm going to do is I'm going to share. Yeah.
Jackie, can you give me 1 minute, since a number of questions are coming in? These Google Hangouts, the only people that can be talking are the TAs and myself. If you want to ask questions, you have to pump it in through the chat window. You cannot join this and have a video and audio. Okay? Sorry about that, but that's how these Google Hangouts work.
Oh, Brent is on.
Yeah.
You should get Brent to introduce himself.
Oh, okay. Brent, you want to say hi? Introduce yourself?
Sure. My name's Brent. I'm a fourth-year grad student at ASU. I research sources of the epoch of reionization at high redshift, which are basically massive star-forming galaxies, and these type of galaxies that have active galactic nuclei, which are basically active black holes that are accreting material. So that's the basic gist of it.
Back to Scott.
I guess I should go now and show the stuff that I've got. So I'm going to do a screen share now. Is that okay, Frank? Give a thumbs up. Awesome. Okay. All right. Screen share. Screen share for Hangouts. Desktop. Start screen share. I am screen sharing. Okay. Hi, Brent's face.
Hi.
All right. Okay. So first of all, if you're in the northern hemisphere, does everyone see this picture of the stars in the northern sky? Is everyone seeing the same thing I see with the pointers and Cassiopeia and Arcturus?
Yes.
Okay, awesome. I can't flip between the screens to see if you're seeing what I'm seeing. So if you're in the northern hemisphere, then one of the most important skills is to be able to find the North Star. The North Star isn't the brightest star in the sky, which a lot of people seem to think it is. It is, however, a pretty decent bright star in the sky. It's barely visible from inner cities. When we're looking for it on the campus at Arizona State University, we can barely find it because it's a second magnitude star, which is because of light pollution in cities. There's so much extraneous light in the sky from skylights and streetlights and cars and the occasional football stadium that the sky is flooded with all this light that makes it hard to see any star that's any fainter than about second magnitude. The magnitude system is what we use to describe how bright a star looks to you, and it's based on your eye. So it's a system that we've been using for hundreds of years, and it's basically scaled to your eye, and your eye is what's called a logarithmic detector, and that probably doesn't mean a lot to a number of people who have been avoiding math their whole lives, but a logarithmic detector, we also measure earthquake strength with a logarithmic detector. The decibel system for sound is a logarithmic detector. Your eyes are logarithmic detectors of light, and so the North Star is something like 100 times, maybe 50 times fainter than a star like Arcturus over here, which is a truly bright star in the sky. And but instead of saying 50 times brighter, it doesn't look 50 times brighter to us, even though it's putting out 50 times less light as detected from Earth. It looks maybe twice as bright as the North Star over here, because your eyes do this little trick. And they do this trick so that they can see really faint things like stars in the sky during the night and really bright things during the day. And the magnitude system is really intuitive at some level because of that, because it's tuned to your eye. But it's also a little bit backwards because brighter things, brighter stars, are usually going to be lower magnitudes. So Arcturus over here is a 0th magnitude star, or a -1 even magnitude star, and it's bright. So you would think low number means a faint star. A low number in the magnitude system means a bright star. So Arcturus is 0 or -1 in the magnitude system. The North Star is +2. And these other stars in the Little Dipper they're third or fourth magnitude. And at a dark site, if you go outside of the city and you go to a really dark place, in Arizona we go to the Grand Canyon, and you look up in the sky, all of a sudden all of these little stars in between the constellations, they start to appear. And your eyes can actually see down to 6th or 7th magnitude, which is actually really, really faint. So now we're talking about over 100 times fainter than Arcturus, maybe 200, approaching 200 times fainter. And these stars are really not a lot of light is reaching Earth from them, but your eyes are able to detect them. If you go back into the city, you start to have a hard time seeing the North Star. But in the city, you can still see the North Star, and you can also see this constellation here, which is the Big Dipper. In the winter, right now, the Big Dipper has actually rotated. This whole mess has rotated around so that the Big Dipper is skirting the northern horizon. And I think Cassiopeia is up right now. Brent, can you confirm that? I haven't taught the labs in the winter in a while.
Cassiopeia, yeah, it is.
Yeah, so Cassiopeia will be up. So Cassiopeia, depending on where Cassiopeia is oriented, it'll either look like a W or a zigzag or an M, but it's 5 fairly bright stars. These 4 over here are brightest, and then this little faint one over here. But they look like either an M when they're over the North Star, or they look like a W when they're under the North Star. Right now they're in their M configuration if you go out at night. And all of these constellations, Cassiopeia, the Big Dipper, the Little Dipper, they're what's called circumpolar. They never set. They go around the North Star. If you're in the Northern Hemisphere, you will never see these constellations set. Other stars that are farther south, they will rise in the east and they will set in the west, like every other thing in the sky. Sun rises in the east, sun sets in the west. You'll see the planets do this every day. The circumpolar constellations try. They rise in the east and they go over to the west, and then they go down around the bottom of the sky and they complete a little circle. So they never actually go all the way down. So they end up always being visible. So even though the Big Dipper isn't technically up this time of year, you can see it down here at the bottom of the sky, even in the winter. And the Big Dipper is really handy for finding the North Star, especially if you're in a city like we are, and you can't necessarily find the North Star just by looking north because it's starting to disappear into the haze. If you can find the Big Dipper, then what you want to do is you want to find the bowl of the dipper. It's sort of like a saucepan cooking on an oven. You find the front of the saucepan, and these 2 stars are called the pointer stars. And they will actually point to the North Star over here. And then once you find the North Star, then you can usually sort of trace out these 2 stars down here at the bottom of the Little Dipper, and then you'll start to be able to trace out these other little ones in here. The Little Dipper, apparently someone curved the handle. Someone bent the handle and they dropped it or something. I don't know. You can also, if the Big Dipper is high in the sky, you can also use the handle of the Dipper to pull this trick called arc to Arcturus, and it'll point to Arcturus. So Arcturus is this big yellow star that floats around the northern sky, and sometimes it's in the east and sometimes it's in the west, and you're never quite sure what it is. And if you can trace it back to the Big Dipper, okay, you've got Arcturus, arc to Arcturus. So that's the northern circumpolar constellations. And I wanted to show you what that looks like in terms of star trails. So this is a picture of what happens if you have a camera and you force the shutter open. So star trails are a cool astrophotography trick where you take a camera, you leave the shutter open, so you don't let it click, and you just set it down and you point it someplace, and then you watch the sky go by. And the stars move in the sky relative to Earth. And so they will leave these trails over this star trail. This looks like about a 2-hour exposure. The North Star is this reasonably bright little gash in the sky that barely moves at all. So you see it's not perfectly centered on the North Pole, but it's really close. In the southern hemisphere, they don't have a North Star. There's just a hole where their South Star should be. This is a picture from the southern hemisphere, and there's a hole in the sky where their star would be. And these stars over here, oh, it doesn't look so bad. No, they're really very faint. Some constellations that we all have in common, let's see, are the winter constellations or southern summer constellations. These will be oriented as if you're in the northern hemisphere. One of the fun facts, when you look at Orion, I think a lot of us can identify Orion. So these are equatorial constellations. These are constellations that you'll see these in the southern part of the sky if you're in the northern hemisphere. You'll see them in the northern part of the sky if you're in the southern hemisphere, and they'll be straight overhead if you're on the equator. We usually draw them this way in the northern hemisphere, but in the southern hemisphere, one of the weird facts about Orion is that he looks like he's rising standing on his head. I can't even describe this to you. You have to take my word for it. The moon also looks upside down. If you're in the southern hemisphere and you've lived your whole life in the northern hemisphere and you watch the moon rise, the man in the moon is upside down. That's really weird. And this is a winter sky constellation, so he's up right now. He has these belt stars, makes him very easy to identify. And then he's Betelgeuse over here, which is a big red star, and then Rigel over here. And all of this will be upside down for people in the southern hemisphere. The blue star Rigel, which is the feet, which is his foot, will be on top, and Betelgeuse will be on the bottom. So this is one of the easiest constellations in the sky to find. It's quite large. And then Orion has his two pet dogs, Canis Major and Canis Minor. And Sirius, which is known as the dog star, is the brightest star in the sky. And sometimes people mistake Sirius and Venus for one another. Venus is quite a bit brighter than Sirius when it's up in the sky. But stars, I think the rule of thumb for telling if you have a planet or a star is stars twinkle, planets don't. So if it's blue and twinkling, it's Sirius. If it's hovering around sunset or sunrise, following the sun, or just ahead of it, and it's not twinkling, that's probably Venus. And then Procyon over here is the major star in Canis Minor, which is basically two stars. It's the world's most boring constellation, and I guess Canis Minor is a puppy. And there's a really good story about Betelgeuse. He was a hunter in Greek mythology, and his dogs, and a relationship that I think he had with Artemis, the Greek goddess of hunting. All of these constellations that we use in this class are based on Greek mythology, and the stars have Arabic names, a lot of them. A lot of the stars will have names like Aldebaran, and you'll see the A-L in front of them because they have, originally their star name was Arabic, and so it has this little A-L, which means the something. And the reason for this is because in the Mediterranean Sea, back in 2,000 years ago, 3,000 years ago, when people were learning how to sail, they used these stars for navigation, and these were a lot of Greek sailors, and they were commuting between the Arabic nations, and so those are the star names and the constellations that ended up getting permanently attached to the sky in all of Europe and northern Africa. So these are some other constellations that are available in the northern sky, and there's this really cool arc of really bright stars going Betelgeuse, Procyon. Then there's the twin stars, Pollux and Castor, the Gemini, the twins, and then Capella over here. Capella for us in Arizona is almost directly overhead. This red line through Gemini and going down to Taurus, this is the ecliptic. this is the line that the sun tends to follow, and also the planets. And the moon will kind of bounce around a little bit more. But the ecliptic is where you'll find the constellations of the zodiac. So the 12, and nowadays it's actually 13 constellations that are in the zodiac will be along the ecliptic. And then here we've got another change so that you can sort of see the northern part of the sky. I'm going to switch over to the southern sky really quickly because there were some questions about how do you find the South Star. And that is trickier. I had it. Where did it go? Finding South. Okay. Okay, so in the southern sky, it's harder because there's no true South Star. And yet you still want to know where South is if you are trying to find your way around. In the southern sky, people tend to use the Southern Cross. And this is the constellation that appears in the Australian flag. And it really is very bright. And again, it's a circumpolar constellation. So if you're anywhere in the southern hemisphere, you should be able to see this any time of the year because it never sets. It'll just go around the south celestial pole. It'll skirt the horizon and it'll come back up. So if you face south, you should be able to see the Southern Cross. And there's also these two stars called the pointers. And a lot of the instructions I have are actually use the pointer stars in addition to the Southern Cross. I think the pointer stars are in the constellation Centaurus, I think. And you can sort of draw a line between the pointer stars and then a line through the Southern Cross, and then you'll sort of create a little pie slice, which will direct you to the Southern Pole. Or you can use the Southern Cross and sort of multiply the length of the Southern Cross times 4. 1, 2, 3, 4. And then you're at the South Celestial Pole. I know it's kind of a pain in the neck, but between the Southern Cross and the two pointer stars, you should be able to find the South Celestial Pole. All right, and that's your quick tour of the sky, and you can ask me more questions, and I'll post answers in the discussion board. And I'm going to end my screen share as soon as I figure out how. Didn't work. And someone else can start talking.
Okay, Becky, you want to take over for a little bit?
Sure. I plan to talk about, there's a couple questions, one of which was about how normal, non-astronomers could participate in science related to astronomy. And honestly, if you type citizen astronomy into Google, there are several pages that have a bunch of different projects. I'm going to post in the discussion some of the ones that I found. But one of the ones that I found that was the best is from Sky and Telescope. I'll just show you guys that real quick. There we go. All right. So this is Sky and Telescope, and it just lists a bunch of very specific projects that everybody can work on. So if you wanted to work on exoplanets, which is specifically what was asked in the discussion, you have Agent Exoplanet here, which is you actually get to search for exoplanets using data from an observatory in California. You can just click here to get more information on that. There are different constellations and calculations that you can use for your computer. I think there's another exoplanet one. Planet Hunters also looks for exoplanets. So there's a bunch of different stuff in the Sky and Telescope. And Planetary Society is more local. So, but there's Planet Hunters here again. And then there's much more general stuff. So I'll post these 3 links, and kind of put instructions on how to find stuff. The other question that I was going to answer is about how astronomical astronomy astronomical research is done. The question was, do we predict things and then look for them, or if there's a bunch of stuff that we see but don't know how to explain? And the general answer is we have both. When we discovered the cosmic microwave background, several people were looking for it because it was like the concrete evidence for looking at like the Big Bang theory. So there are people looking for it, but on the other hand, the people who found it did it by accident. They had a telescope they were going to use for radio astronomy, and then when they used it, there was a bunch of noise or interference that they didn't know what to do with. They couldn't figure out what it was. They tried tuning everything, and then they finally heard about this theory and realized that they had already discovered something that a bunch of other people were trying for. So it was somewhat heartbreaking, I imagine, for the other scientists who were trying for it, because the Nobel Prize went to the people who discovered it by accident. So it's like there were people who discovered something by accident that didn't mean to look for it and didn't know what to do with it, and there were people specifically looking for it. There are a lot of things that we kind of look for. We expect for like different theories, like star formation. We have several theories for that, but we're still trying to see through the gas and dust clouds around where stars are born. So we can't see them, the stars, actually through certain stages. We just have ideas of how it might work. We have a few theories about planet formation, solar system formation, that have a couple holes in them. So we're looking for different systems that might kind of give us an idea of how that works. There are really high energy stuff that Frank mentioned called gamma ray bursts. And we have several theories about them, and we do see them, but we're not entirely sure how they work. So there's a bunch of stuff we know about that we looked for because we knew from our theories it should be there. And then there's stuff that we see in the universe, and you're like, where did that come from? Because that doesn't make sense to us. So there's a bit of both. And I think that was mostly what I wanted to say. Said it a little faster than I meant to. So if you guys have any questions about what we have discovered and have not discovered, just post it in the discussion. And if you have questions on how to get started with the different astronomy projects that you can actually participate in, just post it and can show you some links and give some explanation on how to get started. So I will let Brent take it from here.
Okay. So I guess the one question that was interesting to me was asking about basically which elements were created at the Big Bang. And yeah, it doesn't really seem relevant to this class because it's mostly about planets and stars, but I guess it could probably be relevant because basically everything heavier than helium was created in a star, and I don't know if most people know that. So, I guess I can give like a brief kind of breakdown of how those elements were created without going way too deep into like the physics. So from what I understand and what I've read, basically if you just start off with a universe that's like a quark gluon plasma, super hot and dense, which quarks and gluons are basically the constituents of protons and neutrons. There's 3 quarks in a proton and a neutron. Different combinations of quarks make different particles. They can even combine to make exotic particles like pions, and which are particles with 2 quarks. And so, yeah, just starting with a universe that's quarks and gluons. Oh, gluons are the force carriers, particles that hold quarks together. Um, so you have this big, dense universe that's quarks and gluons, and it's super hot, and they're collapsing under gravity, and then also expanding because of heat. So as the universe expands, it cools, and that allows the quarks to start, well, the gluons and quarks to start interacting, and it cools enough to where that the quarks and gluons can combine and start forming protons and neutrons. And um, after a while, they cool enough after like a longer time, and they form basically um, hydrogen and helium. Um, so the way that happens is the particles I mentioned before, the pions, they actually are what bind the protons and neutrons together. They're essentially just they're exchanging these particles back and forth, which is kind of like, it's not exactly a force, but it's like analogous to a force, which is what's holding these like the neutrons and protons together. So after that is done, after the universe cools enough, you have these elements, and I think that it can, I guess, the heaviest element that's created during this this whole phase of the universe is beryllium, a certain isotope of beryllium, and then which was actually unstable, and it can decay into, I think, helium and hydrogen, I believe. So, and if I say anything wrong and anyone notices, just correct me. So that's basically the heaviest you get from just Big Bang nucleosynthesis, and everything heavier than that had to be created in a star or a supernova. Actually, anything heavier than iron was created in a supernova, because you need to input more energy than you'd get out from the fusion of elements to make iron. So I think that's kind of basic, very superficial understanding of like which elements were created in the Big Bang. So I hope that answered that guy's question. And then someone else asked about some large telescope that's being built. So I'm not exactly sure which telescope he was referring to, because I think there are several being built. Like the ones I know of are the 30-meter telescope being built in Mauna Kea, which probably is going to be built in like the 2020s or something. And then so that's going to be pretty huge. And then there's the Giant Magellan Telescope, going to be built in Chile, I think, which is going to be 7 8.5-meter mirrors. So that's going to be like pretty powerful. I think it's going to be like equivalent to one 22-meter mirror. And I think ASU is going to have possibly some part in using that, some availability to use that, which is really cool, because that means maybe someday the students will get to use it too. probably not me or any of us right now, because it's actually going to be finished in 2020 something, I believe.
They might have been talking about JWST. Do you want to explain what JWST is?
Sure. So JWST is going to be an infrared telescope in space. It's going to be orbiting Lagrange point, I believe. I think it's behind the moon. So Lagrange point is basically like a point where the gravity from like one body kind of cancels with another. So there's kind of like a net zero gravity, or a minimum in the gravitational field around these bodies. But I guess this point's unstable, and it's going to have to like orbit in that area somehow. So JWST, it's pretty much optimized to observe infrared light. It's coated with gold, the mirrors, and so gold is actually it looks red because it's reflecting red light, and it's also highly reflective in the infrared too. And all the instruments, they're all infrared detectors, and it has special instruments that can be used to like do very fine spectroscopy on certain it could do very high resolution spectroscopy, and it can also do multiple objects. I forget what the instrument's called, but basically has these little these little windows that it can open and observe a target very precisely, and can get like all the spectra of all these different objects all at once, which is pretty cool. I don't think any other telescope can do that. There's like you can do like a spectroscopy like a it's called slitless spectroscopy, which basically you just observing a bunch of targets at once, but you're not really focusing on any particular target. It's just kind of collecting everything you can get, and that's usually pretty noisy. But this type of spectroscopy is it's eliminating a lot of other surrounding light, so it'd be pretty much way better than anything before it. And
Okay. That'd be good. Let's go ahead and move it on. There are a number of questions that are coming on the Q&A. So I'll just throw some of them out and see who wants to take what. So one that's going around at the moment is, why do stars twinkle and planets do not? Anybody want to take that one?
I can take that.
Well,
Okay.
I feel like I opened that door.
Oh, go ahead.
Okay.
Okay,
that door.
why do stars twinkle and planets not?
Right.
So it has to do with this concept of angular size that we discussed during the Lab 1. And the angular size, the larger your telescope is, the smaller the angular size that you can resolve. Your eyes actually don't have very good angular resolution. So, Frank, does anyone know what the angular resolution of the human eye is offhand?
Oh,
Not good.
not off the top of my head.
It's not as good as an arcsecond.
No.
So when you look at a pretty image that was taken by the Hubble Space Telescope, basically the Hubble Space Telescope is a 2-meter mirror that is in space. Your eye is about 1/4 of an inch. The relevant part of your eye is not the pupil. I'm going to glare at my little screen here. It's the little black part. It's the iris. Not the iris. It's the pupil. The little black part in the colored part of your eye. Quiet. And
the resolution of a human eye is about 1.
yeah, it's like a quarter of an inch. A quarter of an inch can't compete with a 2-meter telescope. The two reasons we build larger telescopes are to increase our resolution, or decrease it rather, to have finer resolution, and to collect more light. Telescopes are giant light buckets. And the more light you have, the more signal to noise you have on every little galaxy. But if you were to stare at the Hubble Deep Field, which you can Google Hubble Deep Field right now and you see all these little galaxies, if you were to look at it with your eye, that whole thing would be one little speck of blackness, basically. You don't even have enough eye to see the light from those galaxies, but if you could, they would all be in one little tiny dot. So that's what resolution does. Resolution is the ability to pick apart little tiny things on the sky that appear to be really close together. Stars are so far away. They are so very far away that we on Earth, and even with something like the Hubble Space Telescope, are completely unable to see. We cannot resolve their surface features. They are tiny. They are less than an arcsecond. So the sky is 360 degrees around. Each degree can be divided into 60 arc minutes. Each arc minute can be divided into 60 arc seconds. So each arc second can then be divided into, I don't know, start making up units, milli arc seconds. The surface of a star is milli arc seconds across, or less. The biggest one that we know of, other than the sun's right next to us. You don't appreciate how close that thing is, because it's right in the sky and you can see it. You can see one side of it and the other side of it. The only other star that we've been able to do with the best instrumentation on Earth is Betelgeuse. And the only reason we can do it with Betelgeuse is because Betelgeuse is huge. Betelgeuse is reasonably close, and it has bloated so much that if Betelgeuse were in the solar system with us, it would, sitting where the sun is right now, it would engulf the Earth. It would engulf everything all the way up to the orbit of Jupiter. It's so big. So even though Betelgeuse is incredibly far away, it's still a reasonably nearby star. So I just said two things that sound like they don't agree with each other. Betelgeuse is incredibly far away, and yet it's nearby. It's one of the closer stars. It's like 300 light years away or something. Is that right?
No border. No
Yeah.
border.
So 300 light years is close as stars go, but it's still really far. So the best instrumentation we have been able to resolve the surface of Betelgeuse, and only Betelgeuse. Meanwhile, we're on the Earth, and when we're down here on the Earth, when we look at these little pinpricks of light that are the distant stars, and we can't see their surfaces, we're really just seeing individual pinpricks. We have the atmosphere between us and them, and the atmosphere, which good for us because we couldn't breathe otherwise, the atmosphere is boiling constantly, and you notice this effect every time you take a transcontinental flight, and the plane bounces and they tell you to put your seatbelt on. That's turbulence in the atmosphere. That's warm air goes up, cold air comes down, turbulence, and that's happening all the time. And it's like when you look, you can see it. You can see this effect if you light a grill or look over hot pavement in the summer. You can see the air boiling, and you can see that it bends light, and it forms a little mirage look. Light, when it travels through that boiling air, gets bent into that mirage, and that's what causes the twinkling of the stars, because the twinkling of the stars are so much smaller than the little bubble of air that's boiling. So it gets smeared out, and the light gets sent all around. So it hits your eye, but then a part of it doesn't, and then another part of it does, and then another part of it doesn't. Planets, they look also like dots in the sky to our eyes, but in fact planets are really very close. And so even though they still look like dots to us with our crappy human eyes, they are larger than the average bubble of boiling air. And so the surface of a planet, even from Earth, if you put a telescope on a planet, it won't just look like a dot. You'll see the surface. You'll see the red spot of Jupiter. You'll see that Venus is often a crescent. You'll see the Martian polar caps. And that means that the light that hits your eye, even though some of it's getting deflected by this mirage effect, there's always more light from the other side of the planet. So the planet doesn't twinkle because fundamentally you're able to resolve the disk of the star, of the planet. You can see the whole surface of the planet from Earth. And a star is just a polka dot. And it's going all over the place. I don't know if that helped. I can probably do a better job typing, but that was my best shot. Next.
Okay. Let's see. We have another question on a recent discovery of
Planet X.
purported
All
planet.
right, so I prepared for that one. Can we move on to another one so that I can, like, take a break?
Somebody else can answer it.
Oh, okay. I have all the links.
Somebody want to take a shot at the prediction from Mike Brown and company on a potential ninth planet and why that prediction is there?
I've only read a headline about that.
It's fun. Talk about it.
Well, from what I heard, they're just calling it Planet 9.
Who is this buffoon, Mike Brown?
Buffoon? Oh boy.
Oh my gosh! So I actually follow him on Twitter. I'm going to show you the screen share. This is hilarious. Screen share, desktop, start. Okay. So I actually follow this guy on Twitter, and you can follow Mike Brown because he's actually a lot of fun. If you like astronomy, and you're on Twitter, it's really worth following Mike Brown. He's the guy who his handle is Pluto Killer. This is the guy who is responsible for the demotion of everyone's favorite tiny dwarf planet. And now he's trying to replace the planet he kicked out of the solar system with a new imaginary planet that he's calling Planet 9. And the reason I called him a buffoon is because it was part of this the boffins at Caltech. So he actually linked in his Twitter account to this awesome article. So I'll show you the real article. This is the Mother Jones article where someone just had it with, we just demoted Pluto because it was too small and didn't do a real planet's job of taking out the trash. But now the boffins at Caltech are claiming we have a ninth planet after all. It's a hilarious article. And it's really so if you follow Mike Brown's Twitter, you can find that one. But the real article, it was in Science on Planet X, and the argument about Planet 9, which, to be honest, this is the kind of argument they used to find Neptune and Uranus in the first place. So here's Mike Brown on the left. This is the guy who wrote the book How I Killed Pluto and Why It Had It Coming. He's the guy who's responsible. And this is his theorist friend, Konstantin Batkin. And they're making an argument based on the orbits of all the other non-planets. So the reason Pluto got demoted is because we have all these other dwarf planets now. So Pluto is down in here in this picture, in this little blue circle around the sun. So Neptune and Pluto are these two little blue circles down here in the center. So all of our solar system that we've explored to date is inside this little tiny circle that I'm circling. All of these other things over here, on these long orbits, these are known Kuiper Belt objects, and these are why Pluto got demoted. Because some of these objects like Sedna and Eris are actually about the same size as Pluto. They have many of the same characteristics as Pluto, and there's dozens of them, hundreds of them. But Mike Brown noticed that some of them, Sedna in particular, and these ones specifically that we've put the orbits here, they have this set of orbits, a class of orbits. So they're all like siblings. And they're all pointing this way, all of them. And another fun fact is they haven't tilted this figure so that you can see it in the plane of the solar system, but these parts of these orbits over here, it's far away from the sun, are all out of the plane of the solar system. They're away from the ecliptic. These parts, the perihelion points, when they're closest to the sun, are all in the plane of the solar system. And so Batekin and Brown are making this argument that the only way this would happen, and in this weird way where they're all over here and there's nothing over here, is if there was something over here that was quite big, which is an imaginary hypothesized Planet 9, which is nudging them over there. Every time it gets anywhere near them, it pushes them over. And we'll talk about resonances, gravitational resonances, in, I think, the 5th chapter when we talk about Saturn's rings. And then we'll talk about it a little bit more when we talk about the asteroid belt and how Jupiter pushes the asteroids around. But so via gravitational resonances, all of these Kuiper belt objects have been shoved out over here by the gravity of this imaginary Planet 9. And the original article was in Science, and it actually has, in addition, it's got a better version of this picture, and it has like the timeline for how we've actually used arguments like this to discover planets like Neptune. But then we've spent a lot of time trying to hypothesize planets past Neptune, and we discovered Pluto while trying to do this, but Pluto doesn't have enough gravity to have this kind of effect. And that's Planet 9, and it's way far out there. It's so much farther than anything else we have ever seen. And so if it's out there and you want to go look for it, if you're looking for citizen science to conduct, Mike Brown actually also has a page. Where'd it go? Here goes the search for 9 planets. Findplanet9.com. So he's actually put out the parts of the sky where he thinks it is. So if you guys want to go out there and search for it, you can follow the instructions on his webpage. And good luck. You could be the next Percival Lowell. And I'm done.
Okay. We have about 3 minutes. I want to be respectful of people's time. So I will say a few words about your upcoming Quiz 1, which opens tomorrow morning, I think 7 a.m. UTC. So Quiz 1 has 23-ish questions, plus or minus a few. It is composed of material from week 1 and week 2, so both weeks are covered in there. It is a mix of both qualitative questions, like what you will see on the homework assignments, and a mix of quantitative problems, like what you see in the lab. The level of difficulty of these approximately 23 to 25 questions are completely commensurate with what you have in the homework and the lab. So they're not particularly more easy, they're not particularly more difficult. It's about at the same level as what you see in the homeworks. There's a 3-day window from when the exam opens to when it closes, and within any time in that window you can take Quiz 1. It's a timed quiz, so once you start it you have about 3 hours. Not about, you do have 3 hours to finish the quiz. The quiz is designed to be around 45 minutes for kind of a typical AST11X student. So some will finish quicker, some will finish in 20 minutes, some will take the full 3 hours. That's perfectly fine. But there's plenty of time in there for what the length of the quiz is designed for. So 45 minutes typical. Okay, and with that we are coming up on 10 o'clock. We will be doing a second Google Hangout in a couple of weeks, and we're going to shift the time that happens by 12 hours so that we get the other side of the globe. So this one is for one half of the globe, and the second one will be for the other half of the globe. And with that, I want to thank you very much for joining this Google Hangout, and we'll see you on the discussion boards. Bye-bye.
Bye.
And Stopping broadcast.